Hello, colleagues. This is my slightly longer version of my final project presentation video. The topic, again, is automated histopathological cancer detection using convolutional neural network. Let's dive in. So a little bit about the data set. The data set was acquired from Kaggle.com. So it was a challenge posted for histopathological cancer detection, and it comprised about 220,000 histologic images. And they were labeled as 1 or 0, namely tumor tissue positive, tumor tissue negative. And in our data set, there are about 90,000 samples with positive tumor presence. That accounts for about 40% of all the sample images. So our data is slightly skewed towards the negative cases. And all the images are 96 by 96 in its size. Here are some imageries I acquired from the data set to just show you how the histologic images look like. And as you can see, in the tumor negative cases, we can see a more clear cell matrix, and it seems like there's a better homogeneity in those slides versus in the tumor positive case, you see like little blobs here and there in different shades. And I guess our goal of this project is really to train the machine to be able to differentiate those two cases, which is, not that easy to do for humans either. And our model was trained on the AWS P3.2 X large instance. And on top of that, I also leveraged the VGG16 pre-trained image recognition network. And in terms of the coding, I used Keras and TensorFlow GPU. So a little bit about the data pre-processing. In order to train the model, we have to separate our data into training set, validation set, and testing set. And here the ratio is set to be 7 to 1. So a little bit diving into the codes. So we'll leverage the shape of the label, a CSV file, to figure out how many images we have in total. And then we calculate the cut point for the training set, cut point for the validation set, and we generated those directories if they are not already existent. And then we use this split data function to incur this iterative moving process. So basically we're saying we're moving image 0 to image train cut point, all to the data dir and train subfolder. And same thing with the validation data, and then testing data. So after all that operation, our directory file directory should look like this. So we have the project, we have the training folder, the validation data folder, testing data folder, and each of them would have a positive and negative subfolder. And here are the number of cases we have in each of the folders. And then we are ready to specify some global variants. And here we tell the machine image size is 96. And there are 3 channels in each of the images, and the batch size we're using is 64. And then we continue to load the VGG16 model. And then here's a brief summary of how the model looks like. There are quite a lot of parameters there, but they're already pre-trained, so it doesn't add a lot to the computational burden. And then we're ready to set up the model. I'd like to point your attention to this rescale statement here. So notice that all the images we're using in this model training are standardized. So by scale of 255. And in this model training, we're using the binary cross entropy, which is a standard for the binary classifier models. And then we're using a learning rate of 1 to the -5th, and then we're recording the training metric of accuracy. So on top of the VGG16 structure, I also added 2 dense layers. One is using ReLU as activation function, and the last one is using sigmoid function as its activation function for final predictions. And this yields a final number of trainable parameters, about 8 million for our data training. So more technical details. In terms of the model training, we are running the model for 120 epochs, and each of the epochs takes 100 steps. And we're saving, because it does take some time to train this model, we're saving the trained model in the H5 file, and then we're saving the training history in the JSON object as well. So the code is set up in a way, if the model is already existent, it reads directly from the H5 file. Otherwise, it starts the whole training process. As I mentioned before, each of the epochs takes just about less than a minute to train in AWS P3.2x large instance. And we continue to plot our accuracy and losses against epoch, which is a pretty standard diagnostics. So we set aside the test set that the model doesn't get to see at all to test the performance of the final model. And here is the codes that I use to run some of the diagnostics in the test set. First of all, we have to generate the features for the positive images and the negative imageries. So the positive images, for example, its feature matrix would take the dimension of number of test positive samples, image size, and number of channels. And we would predict the probability of this each individual feature being positive from our model using this statement. And then notice that this prediction is a probability. So we have to transfer that probability to a 1 or 0 final verdict of whether or not our model thinks this imagery is more likely to be tumor positive or more likely to be tumor negative. Then we continue to calculate the sensitivity and specificity. In order to do that, we have to acquire the true positive, false negative, true negative, and false positive numbers. And there's a little trick that I used here. So if you sum over all the prediction, the 1-0 prediction of the predictions in the positive cases, and you basically get the true positive numbers. Versus if you sum up all the zeros, you count how many zeros there are in your predictions in the positive features, you basically get the number of false negatives, etc. So with that calculation, we're able to continue to calculate the sensitivity, specificity, and overall accuracy in our test set. I'm also interested in looking at some of the misclassified imageries. And so here I looped over the predicted feature. And then for the positive set, I grabbed the samples that had a 0 as its predicted value and plotted the imagery. And the same thing was done in the negative features. So that helps us to visualize what are the samples that are false positive and false negative, as seen on the slides on the left. So here's the exciting part. Here are the results that we got from training the model and the test set diagnosis. So as you can see, with this 120 epochs training, our training validation loss is tapering off pretty nicely, and we get an equilibrium of a validation accuracy of just about 0.91. And then for running through the diagnostics we ran in the test set, there are just about 9,000 positive cases that are true positive according to the pathologists, and 13,000 negative cases according to the pathologists. And we were able to predict 8,000 of the 9,000 positive cases to be correctly true positive, and then about 12,000 of the truly negative cases to be negative, that is true negative cases. So with that, we were able to calculate the sensitivity and specificity in our test data set to be just about 0.90 and 0.93. Notice that the specificity is slightly higher, which makes sense because, as I mentioned, our data set is slightly skewed towards the negative cases. So our algorithm reasonably is better at predicting negative cases. And then the overall accuracy in the test data set is 0.918, which is pretty remarkable by me. So to conclude, I would say by leveraging very deep convolutional neural networks, we were able to attain a remarkably high accuracy used in this automated binary histopathological classification of cancer tissue presence. So interestingly, there is actually a communique published at Nature in 2017. The whole article is arguing how histology is ripe for automation. And I believe what we found in this practice has corroborated that claim. And remember that I wrote those codes to look at the misclassified cases. I'm also interested in seeing how those misclassified cases would differ. So as you can see in the false negative slides, some of the less stained cases like this one and that one, it probably makes sense for the machine to think there's nothing going on there and it's more likely to be false negative. And versus in the false positive ones, it seems like, samples that had more heterogeneity in itself, like you have this weird shading, this lining, and probably different kind of cell types coexisting in one slide are more likely to be classified as false positive. So it's really hard for a non-professional to understand what the machine is doing wrong there. So on top of the enhancing the data quality, increasing data size, I think it also calls for joint effort between pathologists and data scientists in order to improve the quality of such automated classification algorithms. There are a couple of limitations, and based on which I wrote down a few next steps we can take for this project. The first one, due to the limitation of computational power, I did an experiment with hyperparameter tuning. But in this sample, it seems like 120 epochs is enough for convergence of validation costs. And then, at the same time, I didn't set different trainabilities in VGG16, which may also yield different results. And because we had just about 220,000 images, which is quite a lot of image to process already. So the abundance of data here makes me decide not to experiment with data augmentation, but that's potentially problematic because the data quality, the image size is pretty consistent across our training, validation, and testing set. That might have artificially inflated our accuracy. So I believe further investigation into image data augmentation techniques could be interesting with this data set. And here are the references I referred to in doing this project. With that, I'll conclude and thank you very much.